Hi, in this video I'd like to briefly explain how audio is captured with microphone and saved into a widely used file format, WAV. Then I'll show how to write a very simple Python script that changes the pitch of the audio file based on that information. So in simple terms, a sound is only the change in pressure of the air surrounding us. When you knock on the door, you make the door move a little, which then pushes the air surrounding it a little, and thus changes its pressure in that particular area. This pressure change then propagates through the open space, because the air particles bump to each other, and eventually make it to your ear. And finally, in your ear, there is just a membrane that starts moving in reaction to the moving air around it. And after that, there is a mechanism that makes this information available to your brain. And yes, this is a brain, give me a fucking break. So what does a microphone do? It also has a membrane and a mechanism to somehow capture the membrane movement. I don't want to focus on this part in particular too much, because there are multiple ways how to implement this mechanism. However, you can for example imagine a small magnet attached to a membrane. Near it, you can then have a coil that, as you may or may not know from physics, will pick up those changes in the magnet position and induce a voltage based on it. So you have a way to find out the membrane position now. What to do with it next? Well, it would make sense to store the position of the membrane as frequently as possible so that you could later make some other membrane move in the exact same way and thus produce the same sound, which is exactly what the speaker is. And it turns out that this is exactly what the WAV format is about. Apart from some formalities at the start of the file, there is just a bunch of numbers next to each other which describe the sound pressure or membrane position at that particular time. There is another important information that the WAV format contains, which is called the sample rate. This indicates how often the membrane position was sampled. This is important because when you want to play that file on a speaker, you have to know how fast to switch one membrane position for another. So, armed with this information, how do we change the pitch of a sound in Python? Well, pitch is just the frequency of the sound we have. So one way to change the pitch would be to just play the sound n times faster, so that if you focus only on the sine wave, it gets kind of squished and thus the frequency gets higher. One other thing to note is that the value of n is not actually the number of notes we want to go higher. It turns out that the individual notes on our piano are not spaced by the same amount of hertz, but rather are multiplied by 1.06. I don't want to go much deeper on this, but the reason in short is that both our perception of the pitch and also of volume of sound is kind of logarithmic. So what is the problem with just playing the sound file faster? Well, the problem is that it becomes shorter. So how do we fix that? We basically copy some of the values so that we can make the file longer and also less quality, and when we play it faster, it still remains the same size. Let's see this in actual code. I'm using a library called SciPy to load the WAV file into a NumPy list. So here is the logic. When we want to change the pitch by a positive number, this branch gets executed. In this for loop, I am iterating through all of the membrane positions, and every couple of numbers I am copying the current value, as explained earlier. But how often am I copying the value? The expression above is used to compute this value. It is derived from a more important value, which is how many samples do I actually have to add in order to compensate for the sound file speedup? And the answer is, well, as much as you are speeding the song up. So if I'm changing the song by n pitches, the new number of samples should be the old number of samples times 1.08 to the power of n. Then you also need to change the sample rate, which is ultimately the same as speeding the song up. And you do it the exact same way as the computation before. The new sample rate is the old one times 1.06 to the power of number of the pitches. What do you do when the pitch change has to be negative? Easy, instead of speeding up, you slow it down. And similarly, instead of copying samples, you remove them. So now let's hear how it actually works.